Hi everyone, I'm Tom Maccarone. I'm a faculty member in astrophysics here at Texas Tech University. So a total solar eclipse is when the moon passes between the Earth and the sun in a way that keeps us from seeing any light from the main part of the sun. Okay, so in order to have a solar eclipse, what you need is to have the moon closer to the sun than the Earth is. So you need all three of the Earth, moon, and sun to be in a line, and you need the moon to be in the middle part of that line. Right? And that's what happens when we have a new moon. So if you think about that configuration, the moon doesn't emit any light of its own, it just reflects sunlight. And so in that case, the part of the moon that's reflecting sunlight is the part of the moon that's pointed towards the sun and away from the Earth. Okay, so this is an interesting thing that I think we realize because of solar and lunar eclipses. And what that is that for the most part, we think of everything in the solar system as being in one plane, but it turns out that there are slight deviations from being in the plane. And so not in every orbit, when the moon gets to the phase of the new moon, is it exactly aligned with the Earth and the sun. Right, so sometimes it's a little bit above, or sometimes it's a little bit below. Okay, so if you were standing on the moon and looking at the Earth during a solar eclipse, it would be very similar to if you're standing on the Earth and looking at the moon during a lunar eclipse. Right, so if you're standing on the moon and you're looking at the Earth, you'll see the reflected sunlight from the Earth. Right, and then as the solar eclipse starts, parts of the Earth will start to get dark, and when you get to the totality of the eclipse, you wouldn't see that the Earth was there anymore. No. Okay. So it's much more dangerous to look at the sun during a solar eclipse than it is to look at the sun during normal daytime. And the reason for that is that your eye adjusts and the pupil of your eye opens or closes based on how bright it is. Okay, so if you look at the sun during a solar eclipse, your eye thinks it's dark out and your eye will start to close up. But it turns out that not all of the light coming from the sun is visible light. The sun also emits a lot of infrared light and ultraviolet light. And your eye doesn't respond very effectively to those, but they still get into your eye and they can damage your eye. So what'll happen is your eye will open up because it's dark out, but the ultraviolet light from the sun is coming mostly from the solar corona, which is this region that's outside the main disk of the sun, and the ultraviolet light is still coming in. And a lot of the infrared light also comes from the corona. And so those will get into your eye and there'll be some risk of damage to your eyes. Okay, so scientists are interested in solar eclipses for many different reasons. Okay, so and there's a range of different kinds of scientists that are interested in eclipses. So I'm an astronomer, and to astronomers, there are a couple of major things that we're interested in about solar eclipses. So one is the ability to study the solar corona. So the solar corona is this region of very hot diffuse gas that's above the main part of the sun, and it can extend out to many times the size of the sun. And this is a region that we don't understand the physical processes in very well. We're pretty sure that some kind of magnetic effects are heating up this very thin gas, and it gets up to temperatures that are much higher than the temperatures on the main surface of the sun, that are actually close to the temperatures at the center of the sun. And so if we want to make good measurements of the solar corona, a solar eclipse is one of the few chances we have. People can build instruments that will block out the main disk of the sun, but they have a hard time building those in a way that doesn't also block out part of the solar corona. And the moon turns out to be just perfect for doing this kind of work. Okay, so the other thing that's interesting to astrophysicists, and this goes to probably the most famous solar eclipse for scientists. Back in 1919, Einstein had proposed his general theory of relativity already, but there hadn't been any really good observational tests of the theory. And a guy named Arthur Eddington came up with this idea that what you could do is you could look for the motion of stars due to moving through the gravitational potential of the sun. So if you have a star that's very close to the sun, its position will get deflected by gravity. Now, normally when you think about that, that's an impossible experiment to do, because you'd have to see a star very close to the sun, you'd have to be able to observe a star during daytime, right? And the only time you can observe stars during daytime is during a solar eclipse. And so the first really good observational test of Einstein's theory of relativity was made during the 1919 solar eclipse. Okay, and this is something that's of special importance to us at Texas Tech too, because we have heavy involvement in our astrophysics group with my colleagues Alessandro Corsi and Ben Owen in the Laser Interferometric Gravitational Wave Observatory, which is making much more high precision tests of general relativity. And other groups of scientists that are interested in solar eclipses are atmospheric scientists, who can see what happens when all of a sudden the radiative input to the Earth turns off, and see how much the Earth cools off during that short amount of time. And behavioral biologists who can see how animals react when the sun turns off during daytime. So, at least from my perspective, the most famous total solar eclipse is the 1919 solar eclipse, in which Eddington's experiment on how to test the general theory of relativity was done. And during that eclipse, what they did was they looked at the positions of some stars that would normally be so close to the sun that you couldn't see them. And the advantage of that is stars that are very close to the sun have their light moving through the deepest part of the gravitational potential well of the sun. And in the general theory of relativity, we learned that mass causes space-time to curve, and that will also cause the paths that rays of light follow to curve. So normally in a vacuum, a straight ray of light should continue to move in a straight line. But when we add a gravitational field, the path that light follows becomes slightly curved. And the only case that we had in early days where there was a strong enough gravitational field to allow us to see that curvature was the gravitational field of the sun. And the problem, of course, is that normally stars that are really close in position on the sky to the sun are also going to be too faint to see, because the brightness of the sun swamps out their light. During a solar eclipse, when the moon blocks out the sunlight, now you can actually see stars during daytime, and you can make measurements of positions of stars that are very close on the sky to the sun. Well, this eclipse is the first total solar eclipse that we've had going over the continental United States since the late 1970s. And so it's the first opportunity for an awful lot of people to have a chance to observe a solar eclipse. Okay, so I enjoy studying astrophysics because it gives us an opportunity to understand some of the deepest mysteries of the universe under the most extreme conditions. And I enjoy working at Texas Tech because it's a wonderful environment, and I have great colleagues that I can work with. Get enough sleep. Okay, so I would say the main things to do are to do well in your introductory math and physics classes, because you need that foundation in order to do everything else. And then the other thing to do is to try to develop some comfort with computer programming, because nowadays in modern astrophysics we're generally working with very large data sets, and if you want to be able to analyze those data sets, you need to do that with computers.